for having me here. So we're going to switch gears a little bit, and we're going to talk about observations. And I'm sure observations of shocks and what we can learn. So I'm sure that everything I will show is going to look a little bit primitive compared to the level of detail you're used to when compared to your plasmas in labs, especially, but please bear with me. So I gave a very, very detailed focus title, but then I thought it would be good to give you a little bit of a broader overview about what we have been doing and trying to see what type of shocks we observe in our transients and what we can learn from them. So we do have a lot of opportunities to observe shocks in nature, and we go from systems like novae, so white dwarfs that are accreting from stars, to stellar explosions, to tidal disruption events, which is, so maybe let's put it here. Can you hear me better? Yeah, all right, thanks. So we have tidal disruption events. So when a star gets too close to a supermassive black hole, it gets destroyed, and sometimes they come with jets. And we also have a completely new class of transients. They are called fast blue optical transients, a name that well describes how they look like, but when we have those names, it means that we have pretty much no idea what they are intrinsically. Here, I just put an accreting system because I think that's the most likely situation, and that is a new type of astrophysical transient that is capable of launching relativistic shocks in the environment. We have the very well-known long gamma bursts with their very powerful shocks, and then we have our beloved neutron star mergers and short GRBs, pick your favorite name. So we span a huge variety of speeds. So we have this opportunity to study a huge variety of shocks with different velocities. They propagate into different environments, and they map different types of transients. So a good way to visualize their diversity that I like is this phase space where you have the kinetic energy that is coupled to your shock versus the velocity of your shock. And if I place the transients I just talked to you about on this plot here, where they land, you have your normal stellar explosions. They're the non-relativistic shocks, pretty much spherical. You have your long gamma ray bursts, so highly relativistic jets. You have the world in between that until now was very, very difficult to populate. Actually, everything we had before the launch of the Einstein probe is on this plot versus 80,000 of these ones and hundreds of these ones. Now, the Einstein probe is really helping us populating this world of mildly relativistic shocks. Just to remind us that the types of emitting region changes, so we go from spherical to collimated jets, and the amount of mass that is coupled to that emitting region also grows in that other direction. If you place tidal disruption events on the same plot, you can see that they span the whole range. They go from spherical, non-relativistic, to all the way to highly relativistic and jetted. And if you now place the fast blue optical transients, which we were able to characterize just in the last few years, they also span pretty much the whole range. So they are capable of populating this entire phase space as well. So now, why do we like this type of transients for shocks? The main reason, one of the main reasons, is that they allow us to actually study the fastest of all, the ultra-relativistic shocks. And however, and also the other reason is that transients compared to your AGN, for example, they allow you to have a cleaner experiment. What I mean is that when I see a transient, something is happening at that point, so I do have the T0 of when I launch that shock. I have a pristine environment around me versus instead AGNs, which are way more complicated. However, to enjoy those two benefits, we also pay a price. The price is that these things are rare. They don't happen in our galaxy, so I have to go away from our galaxy. There are extragalactic sources, and at that point, they are pretty much point sources for me. So that's a huge price that I'm paying. However, keep in mind this point, which is they look like point sources, not resolved, because at the end of this talk, I'm going to come back and show you how what we are doing to actually solve this issue and try to resolve some of these sources. So for all of these transients, the shocks that I'm going to be talking about is the shock between the ejecta and the outside environment. So all of these shocks are actually pretty much collisionless shocks, and they are actually two shocks at the same time. So a typical situation is that we have a forward shock that is running into the environment. So we have a shocked region that contains shocked material that was left behind by, let's say, a star before explosion. And then we have a reverse shock that is allowing us instead to see emission from the shocked ejecta. Astrophysically, I love that we have two shocks because it allows me to learn both about the environment, so which is the past, if you want, of my transient, and it allows me to learn about the ejecta. So it allows me to learn about what is the explosion, what does it look like. And so astrophysically, I like that I have these two shocks. However, if instead I try to invert the inference and then try instead to learn about shocks instead of using shocks as probes, I start to like the fact that I have two shocks radiating in the same band way less, for obvious reasons. Then to complicate further the issue is that not only I have two shocks that are emitting, but I also have different radiative processes that are producing radiation at the very same time. So by now, you do understand that why it's so complicated to try to actually learn something fundamental about shocks, because I have all of these unknowns. So what do? There are two approaches that we're using, and they are based on these two items. The first is we try to acquire truly panchromatic observations. And when I say that, I really mean it, from the gamma rays all the way down to the radio frequencies at the same time. Why? Because those different radiative processes that will dominate at different parts of the spectrum, and so you can solve for model degeneracies. And the other item is the simplest of all, choose a simple system. And what do I mean with that? Well, first of all, I want to avoid systems where both shocks are producing radiation at the same time. I want to have a system where one shock, I know that one shocked region is dominating. I also would like to have a well-behaved density around me. What I mean is that the simplest possible environment, not something that has a lot of features. And also, I would like to repoint systems where I have a reasonable knowledge of the emitting region, meaning, do I know that I'm looking at a jet, most likely, or do I know that I'm looking at something spherical? So this is what I mean with simple system. Just to give you an idea of what is not a simple system, I'm going to use a tidal disruption event. In general, tidal disruption events, if you want to study shocks, are bad ideas. They are amazing objects astrophysically, but not for shocks. Let me give you 2 words about it. So here is an example of a tidal disruption event that is very close to my heart right now. It's amazing from an astrophysical perspective because it's off-nuclear, so it's not coming from the supermassive black hole at the nucleus, meaning there was another supermassive black hole that we didn't know about just next to it. However, even if we did a really good job in terms of observations, this is good job for radio and all the way to the millimeter. Even if we did that, we are left with a bunch of viable models. This is fundamentally because of 2 things that happen in TDEs. First, we do not know what is the outflow that is producing that radio emission. I have many sources of outflows when the supermassive black hole disrupts a star. I do not know, and with me together is the entire community, we don't know what outflow is producing it. We don't know if there is a single outflow producing that radio emission. Second reason is that in tidal disruption event, the X-rays are not powered by shock. They are accretion powered. That means that I can't use those X-rays to solve for any model degeneracy. Those are the 2 main reasons why TDE are not great choices for shock physics. But let me give you one example instead of what is a good one then. Well, a good choice, a potential good choice, are your vanilla type supernovae. So the most boring is a supernova. The best it is to learn about shock physics. Basically, that's a trait. So what you have there is a typical spectrum, a radio spectrum of our supernova. I picked a particular ordering of the synchrotron frequencies. And I listed here our unknowns. Kinetic energy of the shock. P for me is the index of the electron distribution. So the n in d gamma goes like gamma to the minus p. Density, epsilon b, amount of post-shock energy, fractional post-shock energy that goes into B field. Epsilon e, amount of post-shock energy that goes into relativistic electrons, the parallel only. And let me put this into brackets, distance and time. So you understand that if I want to measure all of these quantities, I better measure all the break frequencies. Otherwise, I will not have parameters to actually solve for it. And I want to pay particular attention to these two guys here, because in our world of transit observations, these are really the wild beasts that we really, really, really hate. So now if you look at some data, this is a normal supernova, you can clearly see immediately that I don't have all of those breaks. I only have one in my spectrum, so that means that it seems like I'm back to the problem of not being able to solve for all my unknowns. And if we look at the evolution of a radio supernova with time, that's how they look like. They're just like bell-shaped spectra cascading down with time. The one thing that we can do is to measure the optically thin spectrum, that slope right there. And for your average supernova, it will almost always be like a nu to the minus 1. And if you're like, why would I care? Because that nu to the minus 1 maps into a measurement of the parallel slope of your emitting electrons. And if you do numbers, that corresponds to a p roughly 3, which for many years has been a problem, a challenge, because it deviates substantially from the DSA predictions of p roughly 2-ish. And here I'm referring to the literature of Damiano and Rebecca for their solution to this steeper spectra that we are seeing. Let me take a little bit of a digression on these p values. So that is probably the value that we can measure the best in our spectra. And we are starting seeing trends. So the trend goes as follows. Young supernovae, when I say young supernova, I mean few years old, so not a supernova remnant. They typically show steep P's of 3, around 3. If you go to your non-jetted tidal disruption events, they show this spectra and or steeper. If you go to your F-bots, fast blue optical transients, so they also show this steeper spectra. If you instead look at your gamma ray burst, the ultra-relativistic ones, those are way closer to the P equal 2-ish that was expected. And if we look at old supernovae, like let's say 10 years old supernovae, this used to be 10 years old, then we go back to P2. So there are twiddle here because I didn't want to commit to a precise measurement. But what we are doing right now is to quantify these differences in the values of P as a function of the shock velocity. What I'm saying is that we are now, for the first time, in the position to try to quantify a potential relationship between how steep is that electron spectrum and the velocity of the shocks that we are dealing with. But here is where some issues come into our game. So great, I can measure this slope, but as you can see, this spectrum is very simple. It's just a broken parallel. So I can only measure a peak flux and a peak frequency, and that's it. So I have 2 parameters, so I can only infer 2 parameters. And here I decided to infer the B field that is responsible for the synchrotron emission and the radius of the emitting region. And I explicitly added here the dependency on these epsilon parameters. You look at this, you look at the powers, and I'm very happy about this one because it's almost not dependent, and reasonably happy about this one too. So I feel like, okay, maybe I don't know anything about the epsilons. I parameterized my ignorance with those 2 parameters, but all in all, I'm happy. But here is when things start getting way less good. So if I try to infer how much internal energy I have, or how much density, just look at that m dot as a density parameter. So you can see that now my powers are much larger. And if you do here the exercise of saying, well, let me assume epsilon E's and epsilon B's are way more in line with what the theorists tell me, well, I would infer really different parameters. So this is to say that for us, transient observers, this lack of knowledge here does translate into a huge uncertainty, no matter what the papers that you will read will say. So typically, this uncertainty is always hidden. Let's just say one word, we assume epsilon E blah, epsilon B blah, and then from that moment on, that is going to be it. So the things become even more complicated because when we do a good job and acquire observations across the spectrum, here I chose gamma ray bursts, for which really we did cover from gamma rays all the way to the millimeter. What we are finding in many cases are not only that the epsilons are 0.1, but we also find deviation, large deviations from equipartition. So anytime we can measure the epsilons, we always find deviations from this equipartition. So this is to say that if you don't remember anything from this talk, which is sort of okay, but if you don't remember anything, the one thing I would like you to retain is that any guidance that you can provide to us observers in terms of, oh, if you see a shock with this property, you should get these epsilons, or this is how the epsilons should evolve with time, as I was chatting 2 minutes ago with Lorenzo, that would be extremely precious for us. So anything you can give us, it will be really, really important. In the meanwhile, we will keep trying to get to our best observations. Here I want to emphasize the millimeter sky, so ALMA frequencies to understand each other, and the hard X-rays. And let me show you how do we play that game. So what we do is very simply said, we have an interest in transient, we report anything we can. As you might guess, it's technically challenging and very expensive to do so. However, when we succeed in acquiring those observations, the rewards might be actually huge. So here is an example. I'm going to use a young supernova, 23IXF. So we're talking about the supernova. So the situation is, as I said before, those two shocked regions that are source of the photons that I'm detecting. But here is the beauty for this young, strongly interactive supernovae. The beauty is that both the X-rays and the radio for this particular type of transient, they are both coming from the same emitting region. So that's the point I just said. They are coming from the same emitting region. But the beauty is that the X-rays are coming from the thermal. They are mapping thermal electrons in that emitting region, while the radio is mapping the non-thermal population. So the reason why I like it is because in principle, we are, for the first time, I would say in the past, there's something that happened in the past few years, we are in a situation where we can say something about the entire distribution of electrons that are in the shocked region. So from a radiative processes perspective, if you like that, this is what it means. So the radio is synchrotron and is here. Of course, synchrotron is everywhere in the spectrum, but because of the strongly interacting requirements that I added to my supernova tag, this means that the densities are high and Bremsstrahl alone can totally make the synchrotron negligible. Okay, so this is what we did for the supernova 23IXF. This is how observations look like, the beautiful synchrotron emission from in the radio, and this is the Bremsstrahl spectrum in the hard, from soft to hard X-rays. And as you can see, when we combine the two type of information, we can actually start understanding what epsilons are we talking about. And for one of the first times in the supernova literature, we actually start agreeing with very, very low epsilon B's. Typically in supernova, we just say 0.1 without any theoretical reason to do so. Let me tell you a word about what has enabled this just in the past few years. And the answer is hard X-ray observations. So if you are a soft X-ray astronomer, usually you take your spectrum and effectively you end up with half of a story. So you have this data. This is a typical, I think those are Chandra data. And then you have this big question mark because every temperature is a branch channel spectrum, and you can see there is no way I can tell what the temperature is. But if I repoint NuSTAR, then NuSTAR is going to tell me about the other half of the spectrum, thus allowing me to break the model degeneracy. So NuSTAR and Chandra together are allowing me to measure the temperature of the shocked electrons that are emitting in the region. So the universe has been kind. I produced a very nearby supernova, 7 megaparsecs, is really around the corner in the world of supernovae. And that allowed some of the most wonderful coordinated soft and hard X-ray observations. And this delta T is 4 days since explosion. As you might guess, this rapid repointing is actually something technically challenging, but we were able to do it. So why that is important? Well, I can understand properties about the absorption of my system relevant to this community. I can measure for the first time, finally, I have an idea about the temperature of those emitting electrons. And from the normalization, I have an idea of the emission measure, which is an idea about the density of the emitting region. So we can measure bolometric outputs from these shocked electrons. We can measure temperatures of the emitting region and their evolution with time. So I'm now in the position to start even asking the question, are the electrons in equipartition with the ion or not? This was totally not a question that we could ask earlier, and I can also map the density as it evolves with time or with radius. So once you demonstrated once that you can do something, it's always easy to ask to your favorite telescope director to give you more time. And then we were able to repeat our experiment other 3 times. So we have now a sample of 4 supernovae. And I just want to draw your attention. This is 2.5 days after explosion. This is the earliest temperature measurement that we have of the shocked electrons in a supernova, normal supernova. So we play the same game, and again, I have this beautiful plot where now we can start even talking about what is the electrons of these, the temperature of these electrons, and you can see that those are hot. There's, let's say, 60 keV, and this is screaming out loud. That is actually my assumption that these were electrons in the forward shock region is actually correct, because otherwise their temperature would be like keV-like. So the other very, very, very simple system that we have been given by nature is something you've heard about for sure, is this neutron star merger 170817. Fortunately, after so many years, that's the only one. And so I call this my after dinner job because you can actually live on this. So in this case, the system is particularly simple. It's simple because 2 neutron stars, the environment around 2 neutron stars is extremely well behaved. Think about the difference between 2 neutron stars, a system of 2 neutron stars versus a massive star. Massive stars can go through a number of eruptions, their environment is all messed up. Neutron stars, they did all of that many, many, many years ago, so around me I have a very well behaved environment. So, of course, was the first and only GW source with the M counterpart, so we did all the possible observations that we could. And here you have a plot, the spectral plot, F nu versus nu. And you can see this is the radio, this is the X-rays, and then you have the optical that at the early times is dominated by the kilonova. This is where we are producing gold. But you can see that starting at 100 days, the entire spectrum becomes the simplest possible thing you can think of, which is a straight power law. And more to this point, it stays like that all the way to when we could measure it around, let's say, 900 days. So we have a system that for 900 days kept self-consistently the very same slope of the spectrum. So I can measure this slope with unprecedented precision in the world of transients. And if you play the same game, that means that I have a very, very accurate measurement of the slope of these emitting electrons. It comes out this 2.15 value, and this is as good as it gets in the world of transients. So, however, I pay a huge price because my spectrum is very simple. Great, I can measure P so nicely because I have 8 orders of magnitude in frequency. However, I don't have break frequencies. That means that everything else that I was hoping to measure, I have basically to give it up. So we pay this price. How do we get out of this issue? The answer is VLBI, very long baseline interferometry. And the key to actually solve partially the system of 1717 was that we could actually see the movement of the emission from, you can see that the centroid is here, day 75, this is radio, and then it moves day 230 to this other position. And that allows me to infer the dynamics of what is emitting, and from this measurement, I can actually say that at this time, the Lorentz factor of the shock is 4, and that allows me to solve, I'm basically anchoring my dynamical solution to that point. So let me say just one word about VLBI. So inspired by 1708-17, and because honestly VLBI has been really underutilized in the world of transients, we decided to put together a VLBI large survey of transients. Has been approved last year as an NRO large project, where our goal is to resolve transients. Why? Because if I resolve the transient, I have a measurement of the size, and I get rid of that parameter in my modeling. To give you an idea, there are around 9-ish supernovae that have been resolved in the history of humans out of 80,000 supernovae that we know of. And in the world of TDEs, I think that people will say that there's not been yet a bona fide TDE that has been resolved. There is 0 plus minus 1. So our goal is to resolve the systems, and that will actually allow us to learn about their dynamics and improve our model constraints. This is why in the opportunities that I think are there for us in the spectrum, I listed VLBI together with NuSTAR. This is really a new window on stellar explosions that we're having. But the last thing I'm going to say in the last 30 seconds, because I know I'm pretty much close to the end of time, is about UVEX here. So at the very beginning, I told you that I was just going to say something about the shock that is born because of the collision of the ejecta with the environment. That's a collisionless shock. However, before that shock, in the world of supernova, there is another one that is radiation-mediated shock, which is the one that is basically responsible, partially this. This is a shock that is basically plowing through the supernova, the star mass before explosion, and then it dies off as soon as it can release its radiation, and that's what we call shock breakout. The reason why I'm bringing this up is because UVEX, which is hopefully a MEDEX NASA mission that I should say is being selected for launch, and we were ready with everything with launch in 2030. UVEX will actually be able to provide information about the transition between the radiation-mediated shock and the collisionless shock phase. And that's why we are particularly excited. To give you just a 10 seconds info, UVEX can repoint in around 3 hours. So it can view on target and start getting observations over 3 hours with roughly the same quality of UV spectroscopy for transients as HST. Right now, HST, if all the stars are aligned, can repoint in 48 hours, to give you a term of comparison. So this is my last slide. So clearly, I mostly talk about work in progress. So there are definitely a lot of challenges when we try to invert the inference and using transients and try to say something about the shocks behind those transients. And I'm not going to hide all the models that we're using to interpret the radiation that is coming out from this transient are highly simplified. Why? Mostly because the observations they were kind of sparse, so they did not require more complex models to start with. However, right now, we're really making substantial progress, and by opening up new windows of observations. So that is motivating us to add more complexity to our models. So this is my main message here, is that any tighter collaboration, any sort of more direct communication between plasma community and transient observers, I think would benefit the world and field of observations of transients immensely. And to facilitate that, we just started at Berkeley. New center is a multi-raptor, just because I love dinosaurs, so I have to find a word. Yeah, that's it. Just a little bit of advertisement. Thank you.
Any questions from the audience? Maybe a quick question. What is the multiraptor going to do?
So the acronym is right there, but the multiraptor is a four-winged dinosaur that could not fly.
That I know, but what will the center mean?
The center is supposed to bring together people with different expertise. So the idea is that we have many different people at Berkeley that do transient in different flavors, and we would like to have a more formal way to collaborate, and at the same time to expand that to other people outside Berkeley. Yeah.
Great. Lorenzo, yes.
Yeah, I was wondering whether, I mean, maybe it can be in the case of GW 17 maybe the question can be a little bit more general, but can we turn the problem around and saying, oh, we absolutely trust the plasma physics controlled parameters. Is there any way we can use this to infer a viable density profile or explosion energy as a function of time? So allowing time dependence or spatial dependence for the parameters that are not microphysically controlled. Is there even a viable solution that can get out of this?
Yeah, I actually do not know the answer to that question because I think that the experiment has not been done. So the only thing that we did is actually with you when we tried to go from the p value that we were inferring to a statement about the shock, the gamma of the shock, and yes, if you do that, you end up with that mildly relativistic gamma 3 to 10, which agrees with what VLBI said, and this is as much as we did. But I think that the future is going in the direction that you're saying.
Yes.
So I think you said at the end about the new satellite that would be able to turn very quickly.
Yes.
So is that, forgive my ignorance, is that so that you can then make the observation much faster at the earlier time? And so my question is, would you expect there to be, because it seemed like a straight line for how things were decaying with time, are you expecting there to be some exciting different thing to happen early on in time?
Yeah, so I went way too fast there, but basically the idea is that if we talk about, for example, about stellar explosions, you have a first shock that goes through the matter in your star, and then it emerges, that is a radiation-mediated shock, and then there is a transition, that shock dies out, and then a collisional shock is reborn when you start shocking the CSM. That transition is supposed to be interesting. And that transition is supposed to happen on a time scale of hours to 1 day, maybe less. And that's why having a spacecraft that can actually do in place as soon as I want is wonderful. Yeah. So to map that particular transition. But in general, the world of observations is all about opening new parts of the parameter space. So the fact that you have something that finally can repoint in less than 70 hours means that I can look at things that I couldn't before. And that's why it's exciting, yeah.
I have a couple of questions. So do you ever see reverse shocks in these transients? And
yes, we do.
What is the signature of that, and how do they accelerate, if any?
Yeah, I don't know if I put the right GRB, but in gamma reverse, we do see signatures of the reverse shock. I guess I did not pick the right one. So yeah, we do typically see a signature of the reverse shock at very early times at radio millimeter.
But what about in supernovae?
No. In supernovae, we have no evidence of emission from reverse shock. No. In young supernovae. No.
What does that mean?
Well, I actually thought about it, and actually, if you do numbers, it is actually fine. It's supposed to be under luminous compared to the forward shock. However, and that is true at early times. However, if you look at X-rays, after a while, even the strongly interactive supernovae that I showed, at some point, you see X-rays coming from the reverse shock region. That happens only when a cold, dense shell that was formed between the reverse shock and the forward shock dilutes enough for the X-rays to actually come out. So they are signature. At early times, we don't see them at later times, yeah.
And another question, what are the constraints on the ratio of electron to ion temperature now that you've fitted the X-rays?
Yeah, so you wouldn't, if you take at face value that measurement of 60 keV, then you would infer that you expect the ions to be around 100-ish keV, and that's a ratio. To be fair, I think that what I'm measuring is probably an average temperature. Is not a given that I'm measuring the temperature of the freshly shocked electrons. So I think I'm actually measuring something on a longer, it's probably not, it isn't fair, I think, to say that I'm definitely outside equipartition because of that measurement. That's why I did not commit to it. Yeah.
Okay, great. Dom.
You could, what's the current understanding of P equals 3 and how evolving time? Also, I thought for some F-bot, there's some indication of non-power law contribution. So what is the current status of that kind of thing?
Correct.
From theory.
So for the F-bot in particular, there was F-bot, but in its generical suggestion. There was a suggestion by Margutti where he said, well, you can have something much steeper than the power law if what is emitting is actually a relativistic part of your Maxwellian. So it's true, if you assume that what you're seeing is not emission from the power law, but it's a relativistic Maxwellian, you can fit observation. Do I need to invoke that to fit the observation? My answer is no. So that's first part, answer to your first part of your question. And then the other, I actually like better the explanation of Damiano Caprioli and Rebecca Diesing about a steeper spectra. And their explanation, you should ask them because I'm definitely not an expert here, but the deviation is related to deviation from the test particle limit. So when you basically deviate from that assumption, there is a precursor that is formed ahead of a shock, and that basically makes the shock compression factor felt by the particles being much smaller than the R equal 4 that you expect in a strong shock, and that's how they get to steeper spectra. But you should ask them, not me.
Well, no, it's still a strong shock. They find this thing called post-cursor, which is a wave that moves behind the shock, and it's receding, and that changes the effective velocity difference that the particles are seeing. I think there are other explanations for the same thing. So don't bet your farm yet. Yes.
Thanks. Nice talk. Apologies if I missed it. What trigger are you using for UVEX for the supernova?
So what trigger am I using for supernovae? So pretty much everything, but the idea was ultrasat. So ultrasat being UV emission with large field of view would be the natural source of triggers for us. And we also have internal triggers, but ultrasat is probably, I would say, the main one. We do allow for ground-based and X-rays too.
What's your field of view?
I forget it now, but it's much larger than UVEX has like a 10-degree field of view, a 1-degree field of view, and that is much larger. Yeah, I'm forgetting now. Much larger, and even have a part of the sky where they look always.
Yeah. All right, thanks.
If I may ask one more. So the P to the minus 3, sorry, P of minus 3 that you're seeing, is that a property of trans-relativistic supernova or just any young supernova even at lower velocities?
This is a property of that particular supernova for which we could map very well both the radio and the X-rays. And the shock in that case is a 10,000 kilometer per second shock.
Sorry, I meant the power loss index, not the
P3. It's the same answer though. So it's
okay.
10,000. Pick your random supernova, 10,000 kilometers per second, 2.1 C, They always show peak of 3, always.
Good. Okay. But there, if you could map into a Mach number space, would they be?
I would love to do that. I don't think we are in the situation to do a careful job there, but that's a goal, would be to say, okay, with this P versus this velocity. Yeah. I would love to do it.
All right. Any more questions? I guess we can move on to the next talk. Let's thank the speaker again.